All right. Good evening, everyone. Thanks, Krishna Kumar and Manav, for joining. Um, so maybe we will get started soon. Other participants will join. Let me quickly check my recordings. Okay. All right. So this is our fourth week, and in this week, what we are going to discuss is about turbojet engines, but with afterburners. Last week we discussed turbojet engines without afterburner. This week we have afterburner also. So before I go forward with this session, does anyone of you have any questions? If you have questions, you can quickly ask, or I can complete the session in another 30 minutes or so, and then after that also floor will be yours. You can ask your questions. All right. I assume that there are no questions. Um, Let me move forward with today's agenda. So what we are going to discuss today is we will quickly do a quick recap about turbojet engines with afterburner. Here we saw two spool turbojet engine with afterburner in our week four uh, you know lectures, and also its performance we saw. Similarly, I have one question today, which is going to be, it is not two spool, but it is a single spool turbojet. Okay, we will solve it in today's class. Before we get into class, I wanted to make a few important announcements. One announcement is exam registration. The last date for exam registration is 19th of August, 5 p.m. Um, and we strongly encourage you to take the exam because it actually, tests your capability and also your intelligence based on, like, it also gives us a view that how much you are able to grasp and how much you are able to understand. So um, I would strongly encourage everyone to you know register for exam and just try to give your shot about it. So that is one thing, and also relevant informations you can take from the slides also, or it is available in NPTEL forum. And another important opportunity, I just talked with Professor Chetan Mistry, and he said he will be able to provide a summer internship opportunity for the students who are going to perform well in this course. So you will get an opportunity to do a summer research internship at IIT Kharagpur with Professor Chetan Mistry from this course. So the only thing you need to do is you need to showcase your interest. Okay, your interest in the course, your diligence. Why we say diligence is how much you are invested in this course, and also how much you are interested in this topic is going to uh, reflect on your exam uh, marks and hence your internship opportunity. So uh, it's a very good opportunity for students to work at IIT Kharagpur for 2 or 3 months for their summer internship. So I strongly encourage everyone to uh, take this seriously and also try to achieve your dreams with it. Okay. So this will be, like a starting point of your career if you're more interested in gas turbine or aerospace industries. So um, doing an internship at IIT Kharagpur is not a very easy thing to do. So you have provided with this opportunity. So I strongly encourage you to uh, uh, try to grasp this opportunity. Okay. And one minor note that I wanted to uh, convey here is uh, we strongly encourage you to ask any questions related to the course contents, and you can ask. Actually, we encourage you to ask both in this session also. This is especially for that doubt clearing sessions, and also it's advisable to uh, ask in a common forum. The reason is Professor Chetan Mistry will be answering your questions, and while his answer he replies to everyone in the forum. So in that way, the students who are also having a similar doubt but miss the sessions, or who are not asking in the forum, will get benefited. So we encourage you to ask a lot of questions, and ask in both forums, and also be interactive in this session also. Okay, so a common link to the forum is also given here. Okay. um, with those important announcements, let me go forward with today's agenda. It's a turbojet engine with afterburner. We all know a turbojet engine. Last week we saw. Uh, Here we additionally have a afterburner component in it. And how is this going to help us? This is actually going to provide, augment thrust. We will be, upon adding this afterburner, we are going to get additional thrust. Usually they use it for a short duration of time, uh, only during whenever they require, because it comes with its own disadvantages, you can say. Although it provides a lot of thrust, we will see what are those disadvantages, how it is getting affecting, how it's affecting the performance, everything we will see. But they usually use it only for a short duration of time. And it can also be, the same engine can be, are the same engine size. For a given engine, you can actually add a afterburner and make it more powerful for a duration of time. So that is a one advantage of afterburner, having an afterburner. Additionally, we also need to have an adjustable nozzle, um, and we will also see some numbers why we need an adjustable nozzle. Okay. um, so as usual, in a turbojet engine, we have an inlet, and then air is getting compressed in a compressor, and then it goes through the combustion chamber where fuel gets added, and then combustion happens. And after the combustion, high temperature, high pressure gases, they expand in the turbine. And while they expand in the turbine, the energy is getting extracted from the gas and was given to drive the compressor. And after it comes out of the turbine, we have a low temperature, or low temperature and low pressure gases. And this low temperature gases will usually get expanded in the nozzle if there is no afterburner. Here we additionally have afterburner. So again we add some fuel here, and upon adding some fuel, uh, the temperature raises, and once you have a higher temperature, the nozzle is an accelerating device. It converts a thermal energy into a kinetic energy. So it accelerates to a higher velocity on the exit, which causes, when you have higher velocity at the exit, your thrust will increase. Basically your thrust equation has velocity at the exit, right? So because we have higher velocity at the exit, your thrust will increase, and that is how you augment the thrust upon adding an afterburner. Okay. So this is the basic understanding that we have from the lectures. Let's go forward and try to draw a TS diagram for this. In a TS diagram, it would look something like this. So initially you will have this pressure line P infinity. So let me try to highlight it. So initially you have, so you have this line, P infinity line, and inlet diffuser duct will be P infinity to P2. So the black line here denotes isentropic process, but the red line is the actual process that we encounter in any actual gas turbine cycles. And from 2 to 3 you have a compressor, and during that there will be a very high pressure jump or pressure increase in the compressor from P02 to P03. And from 3 to 4 you have a combustion chamber, but usually it should be a constant pressure, but in actual cycle you will have some pressure losses. So that's why you will go through this actual red line. If not, it would be lying in the same P03 line. Okay, that is something you need to note. And from 4 to 5 you have turbine, and during turbine the pressure decreases, and that's why you see P05 line is below than P04. And from 5 to 6 again you have afterburner. So what would happen here, in addition, so if it is If the afterburner is not there, from 5, it directly goes through a nozzle and the pressure and temperature further decreases. Right? But since we have afterburner, we are adding some fuel, and this is happening at a constant pressure. But in actual, there will be pressure losses. So ideally, you will again see a rise in temperature because we added fuel and combustion is going to happen there. That's why you see a rise in fuel, rise in temperature. And after 6, you have a nozzle, and during, we all know the nozzle, we are going to have expansion of gases from 6 to 9. So this will be your typical TS diagram for afterburner, and depending on whether the nozzle is choked or not, this point number 9 either lie at P infinity line or it will lie a little above, okay, which we will see when we solve a numerical on this. Okay. All right, so I hope everything is clear as of now. So again, if there are any questions, you can stop me anytime and ask your questions. Okay. Moving forward. So this is the question I have. It's a turbojet engine, but with the afterburner. So this is the same question that we solved in the last week also. Only thing is we additionally have afterburner in it. Uh, so uh, let me quickly go through the question for the sake of completeness. A small turbojet engine with a compressor pressure ratio of 8 and turbine inlet temperature of 1200 Kelvin and a mass flow rate of 15 kg per second. So it's a small turbojet engine, and the aircraft is flying at 260 meters per second. Okay, at an altitude of 7,000 meter. So they have also given P infinity and T infinity at that altitude. Now, if the gases in the jet pipe are reheated to 2000 Kelvin, okay, which means after it comes out of the turbine, it enters the afterburner and gets reheated to 2000 Kelvin, and the combustion chamber pressure loss is 3% of the pressure at the outlet of the turbine, which is combustion chamber pressure loss. Calculate the percentage increase in nozzle area required for the mass flow rate to be unchanged when compared with the non-operative afterburner. Also calculate the percentage increase in net thrust. So basically, if you don't have the reheat, you may need to compute what is a nozzle and the thrust, nozzle area and thrust, and upon adding reheat, what would be your nozzle area and the net thrust is what you need to calculate, and you need to find the percentage increase in these two. Okay. um, we have Tushar asking, sir, regarding acceleration and decreasing thrust from cockpit, what behavior we get to see in the engine? Okay, so usually, so okay, you are asking in the cockpit when we move some levers, that's what we see in the cockpit. What exactly happens in the engine? Is that your question? Right. So um, there are only few control variables while operating an engine. Only thing what you have is the fuel inlet. Okay, so when you increase the amount of fuel, the amount of energy release will be high, and your turbine entry temperature would be high. Okay, so ideally this turbine entry temperature is your limiting factor. So uh, when you push the lever up and down, your fuel goes up and down, so your turbine entry temperature goes up and down. And when your turbine entry temperature goes up and down, your thrust also goes up and down. So that is how they change the acceleration and deceleration of the entire aircraft. So that is the main variable. Addition, there are also few more variables. Uh, yeah, but this is the main variable that they usually use it to control. Any system for restarting of engine in mid-air? That's a good question. It's there must be some lot of restarting mechanism. I'm not really sure about, but I will probably get back to you about that. Okay. So usually when the bird strike happens, or for some reasons your combustion chamber extinguishes, uh, they so there are different reasons why your engine will go non-operative. Uh, so yeah, I will get back to you about that. Okay. Yeah, yeah. So that is also one of the reasons. Actually, bird hit is actually even fatal. Uh, I'm not sure. Only sometimes, some cases you'll be able to restart. Some cases it will be damage for the engine. So usually, how they design is when you design a aircraft engine for a when you design an engine for an aircraft. Usually they have these two engines or four engines in the wings. So even if one gets hit by the bird, or for some reasons if it goes fatal, what they will do is they will design the other engine also in such a way that you will get enough thrust at least to land. Okay, so when you have two engines, if one engine goes out, the other engine should be enough at least to safely land and save uh, lives. So that is how they design the aircraft engines also. So whenever you say the thrust is given, this is the maximum thrust it can give an engine. The so the aircraft uh, weight and the amount of engine you require is actually based on if there is some fatal accident happens, there should be an uh, you should be able to land with one engine itself. So they will design your engine based on that, or they will go with a bigger engine which can perform such activities. So that that is how they design it. But restarting of engine, I have to look into it, and I will get back to you, Tushar. Okay, all right. Um, so yeah, so coming back to the question, we have to find the change in area of the nozzle and also the change in the thrust. Um, but for that you need to do a calculation without afterburner, and we need to do another calculation with afterburner. The calculation without afterburner we already did in week 3. So this is the same question, but now I added a afterburner in it. Okay. And additionally we have isentropic efficiencies of different components, and also combustion chamber pressure losses have been given. Okay. Now if I want to, yeah, so this is the given parameters for our question, and also the efficiencies and losses are organized it here. Now we need to find the change in area and thrust, as I said. Okay, so let's go forward. So how do we go forward with calculation is, first we always start from inlet, and we will go through each and every component, find station properties of each and every components. That is, and then at the end we will get V9 and use it for area calculations and thrust. Okay, so first we have inlet. From there we get P02 and T02, which is same as previous classes turbojet engine. And then you have compressor pressure ratios are given, and from there you will get P03 and T03. Once you obtain P03 and T03, you can use it to find uh, fuel air ratios uh, in the combustor, and also to find P0. Okay, and then it goes to the turbine, and then from turbine you can get P05 and T05 exit pressure and temperatures of turbine. And then we have afterburner. In a previous question we didn't have afterburner, we have only jet pipe and with no losses. So this is the only change from previous question to this question. So until turbine there is nothing change from the previous week's question. So anyway we will go through that calculation we quickly go through those calculation till turbine. Okay, and in the afterburner we actually add fuel, so we need to find the fuel air ratio at the afterburner. Okay, and then the gases enter the nozzle, and from nozzle you will get P9, T9 and B9, and use it to calculate area, thrust, TSFC, and yeah, efficiencies, etc. So the first component you have is inlet. We have already seen this calculation, we need to know Mach number with which air enters. So for that, we already know V infinity. So use that to find out the Mach number. And once you get the Mach number, you substitute in the temperature equation to find the temperature and pressure. Okay. So the efficiency of diffuser comes in the pressure, but not in temperature, because we are almost assuming that it is adiabatic process. Okay, from in the diffuser. But in pressure, you will have some, since it's not isentropic, you will have some pressure loss. That's what you will see. That's why you have a diffuser efficiency. So this is a easier way to uh, remember how this formula comes. Okay, and then if you do this, you will have P02 as 63.47 kilopascal and P02 as 278.4 Kelvin. I'm not doing it here because we already did it, so I thought I will quickly go through. We will go through the afterburner part a little carefully. Okay, and then you have compressor. We have compressor pressure ratio. Since we already know P02, you can find the P03, which will be around 5.07 bar, okay, or 507.75 kilopascals. And we know efficiency of the compressor. From there, you can find temperature ratios, T03 by T02. These are all equations you already know. I don't want to waste your time explaining this equation. So if you perform this calculation, if you substitute this, you will have 1.922 as your temperature ratio across the compressor. And from there you can find the temperature at the exit of the compressor, which will be 535.1 Kelvin. Okay, and then you have a combustor. In the combustor, we are adding fuel, so we need to find fuel air ratio, and for that, what will we do? We have to do something called energy balance. Okay, we will look into it. So before that, we will try to find the pressure losses. It's already told that it's 6% of the entry of the combustor is a pressure loss. So if you perform this calculation, you will end up having P04 as 94% of the P03. Okay, which means another 6% is lost. That's the concept. And the P04 would be 477.29 kilopascal. Now we need to find fuel air ratio, which is F, and for that we will use energy balance. This is nothing but what is the amount of energy entering and energy leaving. That's what you need to find out. The energy entering would be air with certain temperature, and also fuel with certain heating value. Okay, and energy leaving would be air plus fuel, combusted air plus fuel as a gas, as a hot gas, leaving the combustor. Okay, that's why you have two terms in the LHS of your equation and one term in the RHS of your equation. Two terms corresponds to one entering as a air and second one as a fuel with a heating ratio, sorry, heating value of QR. Okay, so yeah, so if you rearrange it to get F, which is m infinity by m dot F, this will lead to second, yeah, this will lead to, if you substitute and if you calculate all this, you will end up having 0.0209. You should note one thing here. The air which enters will be with a specific heat of CPC, which corresponds to cold air specific heat, and the air which will be leaving would be CPH. Because it has undergone combustion, it reaches a very high value. The air composition is not same. Okay, so air composition with which it enters would be 79% and 21%, 79% nitrogen and 21% oxygen. But when it leaves, it will no longer be like that. It will have carbon dioxide, it will have steam, it will have H2, it will have O2, and all kinds of various gases. And because of this, your specific heat will be different. Okay, and even the specific heat ratios will be different. So that is why CPH and gamma H should be taken into account properly. Okay, and T04 we already know, which is given to us, which is an input for our equation. T04 is 1200 Kelvin, which is a turbine entry temperature. Okay, so that is how we were able to find the fuel air ratio. And the next component is turbine. And for turbine also we will do energy balance, because whatever the work you extract at the turbine should be given to the compressor, right? And it is also the same logic across the turbine. What is the energy change? That is the amount of work extracted from the turbine, multiplied with some mechanical efficiency, will give you the amount of work given to the compressor. And now here we are assuming the mechanical efficiency to be 100%, which we did in the previous question also, I mean in the previous week's problem. So usually it is around 90% or 90%, usually 90-95%. And here we are assuming 100%, and if you substitute all these numbers, you will end up having T05 as 981.6 Kelvin. So in your entire cycle, there are two places where you will achieve high pressure and high temperature. Okay, the high temperature will always be at the exit of the combustor or the inlet to the turbine. Okay, turbine entry temperature is the highest temperature that you will reach in your entire cycle, and the highest pressure you will reach will be at the exit of the compressor, not at the inlet. So these two, high pressure and high temperature, will not happen at the same station. Instead, high pressure happens at the exit of the compressor, and high temperature happens at the inlet to the turbine. That is how usual turbojet engine or any gas turbine engine will work. But if there is a reheat system, um, the high temperature will happen at the afterburner during the reheat. Okay, so that is our next component. So before that, we also need to find pressure. So this will show us the pressure would be. So you can substitute this temperature quantities, and then you can see the gamma H we have changed from 1.4 to 1.3. Gamma C was 1.4, and gamma H here is 1.3 because of hot gases. And P05 would be, if you substitute all those numbers, you will end up having 183.63 kilopascal. So this is the pressure with which the air or gases enters the afterburner, and the temperature at this point would be 981.6 Kelvin. Okay. Uh, the next component that we have here is afterburner. So this is the calculation that we have to do. The afterburner, and so once you have the afterburner, the nozzle parameters also changes, and hence the thrust and TSFC. Okay. So in afterburner, what you do is, it is same as combustor. There is nothing difference. Only thing is even the calculations are same. Only thing is it enters at lower pressure. So that is something you need to note. In a combustion chamber, the pressure is very high. We saw it's 507.75 kilopascals. In afterburner, you have a lower pressure here. P05 is 183.63 kilopascal because it has already expanded in the turbine. So, and also we also have exit of the afterburner. So, temperature at the exit of the afterburner, which is 2000 Kelvin, which is given. So based on that, we will be able to, we will, use, we will, add fuel to reach this 2000 Kelvin. That is our energy balance basically. So before doing energy balance, we can find the pressure losses. Pressure loss is 3% of the turbine exit pressure. So if you do this calculation, you will end up having pressure loss to be 170. So the, at the exit of the afterburner, it will be 178.12 kilopascal. So you can see from 183.63 kilopascal, it has reduced to 178.12 kilopascal. So now let's do energy balance. In the energy balance, what do we have? We have hot gases. Although it's no more hot, it's 981 Kelvin is relatively cold compared to the combustion chamber's temperature. The gases which enter is at 981.6 Kelvin. Okay, so it comes with some energy, which will be m dot infinity plus m dot f Cph T05. Basically, this term is the gases which enters the afterburner. And what you do is you add some fuel and increase its temperature. So when you add fuel, it comes with some heating value which is Q1. So m dot f, we are denoting it as m dot f AB, and we also have some efficiency, burner efficiency eta V. We will take it same as the combustion chamber efficiency. Okay, and if you this will be the energy coming from the fuel. Okay, the first term is the energy with which hot gases enter, and the second term is the energy with which fuel enters, and these two energy will this only will go out in the other side, right? This is a flow device. So um, the energy with which it goes out will be m dot into cph into t06, where the m dot is the, it also includes the fuel that you added. Okay, so because mass has to be conserved, m dot infinity plus m dot f is the gas which is entering, plus m dot fab is the fuel you are adding. So at the exit you should have all three of this component. So that is what you see here. This is the energy balance. I hope uh, everyone is clear about this. If you have question, please stop me anytime. Okay. um, all right, so given that, you can just rearrange this equation to find fab, and you should note something here. It is m dot infinity divided by m dot fab. It's not m dot infinity plus m dot f by m dot fab. It's always all this f for fab is based on m dot infinity. Okay. um, yeah, I think it should be the other way, m dot fab divided by m dot infinity. I think there is a problem here. This should be m dot fab and this should be m dot infinity, right? Okay, sorry about that. I will update it when I post it in the Google Drive. So it's always weighted with m dot infinity, the air which entered the turbine at the inlet. Okay, even the f, it is also weighted with m dot infinity. So this is the amount of fuel that you are adding in the afterburner, and again, if you substitute all these values, what will you get? So if you have pen and paper, you can do a quick calculation, and you can let me know what you will get. So this is the only change that we have in the afterburner. So this, I mean, this is the only change in the entire problem. So you additionally have afterburner. So if you do this calculation, you will so let me show you the number, check whether you are getting the same number. You will end up having something like 0.0302. Okay, so which is actually greater than the fuel that you added, yeah, in the combustion chamber. The fuel that you added in the combustion chamber was 0.0209. Here it is 0.0302. Although in the combustion chamber you have raised the temperature only till 1200 Kelvin, here you are raising it till 2000 Kelvin, but also it depends upon how much delta T that you are looking. Okay, so yeah, so this is the number that we have here. We will see how, what are the other things it is affecting. Okay, so I hope others are also getting the same results. FAB to be 0.0302. Okay, let me move forward. I assume there is no question at this point of time. The next is we have nozzle. So after afterburner, we have a nozzle. So in the last class, we saw that you know, in a nozzle, we will check whether it has chocked or not. If it is chocked, then we will have a different formula to calculate the pressures and temperatures. If it is not chocked, you will have different formulas to calculate. In last class that we found out that P06 by PC is something like this, and also the nozzle is chocked, and hence your uh, pressure at the exit of your nozzle is 96.83 kilopascal, which is same as the critical pressure. In this, when you have a afterburner, let's see what happens. The same process you should continue. First thing is you should check for choking condition, and for choking condition you have this formula is same. There's no difference just because of afterburner. But only the pressures that you use here will be different. Okay, so last time uh, the pressure ratios, the P06 by PC, if you noted, it doesn't depend on any station properties. It only depends on gamma H, which means specific heat ratios, and also the efficiency of the nozzle, which is same in both the cases at this point of time. So also we are assuming that after afterburner, there is not much change in the specific heat ratio, so we are still using the same gamma H. So ideally, there might be a case that you might have given that after afterburner also your gamma H and CPH can change. Okay, so please note that if there is any change in gamma H or CPH, you may need to take into account in your nozzle calculations after afterburner. Okay, so here we are assuming that there is no change in CPH and gamma H when it goes to the afterburner. Okay, um, so and this changes only happens in combustion chamber and afterburner. It doesn't happen in any other component. Okay, because all other components are not uh, they don't add fuel, or there is no change in the composition of the uh, gases, air or gas. So ideally there will be a slight change because of change in pressure and temperature, but that will not lead to a very big difference uh, that you see in combustion chamber compared to what you see in combustion chamber and afterburner. Okay, so you can take that for granted that there won't be any change in CPs or gamma H while it is going through other flow devices like compressor, turbine, and other uh, jet pipes and inlets, all the other components. Okay, all right. So if you look at this pressure ratios are not pressure ratio is not dependent, so you get still 1.8964 as your P06 by PC. So from here you can find the critical pressure, but while finding this critical pressure, you may need to use the new pressure that we found here after it goes through the uh, afterburner. So the exit of the afterburner, we know there has been a 3% loss in pressure. So that pressure will lead to 178.12 kilopascal over here, right? So this you need to take into account. And then if you calculate the critical pressure, it's going to be 93.93 kilopascal. So there is a drop in critical pressure from without afterburner to with afterburner. And the reason is the entry pressure, the stagnation pressure at the inlet to the nozzle is less. So previously you have 183.63 kilopascal as your inlet pressure. Now that 183 has reduced to 178, so proportionate amount of critical pressure also reduced. So that is the main reason. And still this 93.93 kilopascal is higher than P infinity, which is 41.06 kilopascal. So you will have your nozzle will be chopped. Okay, so still your nozzle is chopped, so there is no change in terms of that. So there's no change in the equations that you use for T9 and B9. Okay, we will see that. So your P9 would be 93.93 kilopascal now. Okay, so without afterburner it was little higher, 96.83 kilopascal. Now it has reduced. Okay, all right. So once you have you know P9, you need to find out T9 and V9, right? And we all know it has chopped. So if the nozzle is chopped, the at the exit you are going to have Mach number equal to 1, and if the Mach number equal to 1, you can easily find out what would be your temperature, right? So this is basically coming from isentropic flow relations. So we all know that how do you write T06 by T9 is 1 plus gamma minus 1 by 2 m square, but we know that m is 1, right? So if m is 1, this is going to be 1, and hence you will have gamma plus 1 by 2. So that is what you have here. Okay, so this is basically This is basically coming from choking condition. So since your nozzle is chocked, you have Mach number equal to 1 at the exit of your engine or exit of the nozzle, and hence you can find the T9. So the ratios will be still same 1.15 because it depends upon the specific heat ratios, but your T9 will vary. Now the T9 will be based not based on 981.6 kilopascal, which was exit of the turbine. It will now be based on the afterburner's exit temperature, which was 2000 Kelvin, and hence your T9 also would be very high. So it will be around 1739.13 Kelvin. Okay, so you can compare these two. When you don't have afterburner, you have only 853.56 Kelvin as your exit temperature. Now, because you have afterburner, you are almost doubled the temperature at the exit. Okay. Um, yeah. So this is assuming one important thing. This is assuming your nozzle is a converging nozzle. So you should keep that in mind. That then only you will have Mach number equal to 1 at the exit of your nozzle, and you will have corresponding this temperature. So usually in a fighter aircraft which has afterburner, they will also try to use a converging diverging nozzle. Okay, so when you have converging diverging nozzle, your Mach number will be 1 only at the throat, and after the throat you will have supersonic flow. Okay, and hence your temperature at the exit will be further lower than what you see here, 1739 Kelvin. Okay, it will be lower than that. And further we need to know what is the exit area. Then only we'll be able to find the uh, what do you call the Mach number at the exit. Okay, once you know Mach number at the exit, you can easily find the velocity at the exit. Okay, so here we are assuming converging nozzle. So I hope whatever I wanted to convey is clear. If there is any doubts, please let me know. Okay, uh, let me move forward with velocity. So the velocity at the exit now would be, I mean, the equation is same because it's a chalk nozzle, but the T9 is different. So it will be, um, so T9 will be now 1739.13 Kelvin. Okay. So if you do this calculation, can you guys do this calculation quickly and let me know what is the V9 you are getting? So if I want to quickly say, your temperature has almost doubled, right? And now V9 is a square root of T. So which means if your temperature has doubled, your velocity will be like square root of 2 times whatever the velocity that you got in the without afterburn. So 544.3. So let me show you the number. So it will be something like 776.95. So please do cross verify this number. I might do a lot of arithmetic mistakes. So 776.95 meters per second is the uh, velocity that you will have. So when you don't have afterburner, you have 544.3 meters per second. Now you have 776.95 meters per second, which is around like 1.42 times the 544.3. So which is equal to root 2, right? So that's what I was basically telling. Okay. So our velocity has clearly increased. So if the velocity increases, our thrust is going to increase. So let's calculate that also. So the next is we'll calculate the nozzle area, and after that we'll calculate the thrust. The nozzle area now in without afterburner we saw that m dot through nozzle is m dot infinity plus m dot f. But now what will happen? The m dot through nozzle will it still be m dot infinity plus m dot f? Can you guys think? So now, in addition, what you have is afterburner, and in the afterburner you added fuel, right? So now your m dot through nozzle not only include m dot infinity plus m dot f, it also should include m dot f AB, okay, m dot of afterburner. So Just to have a difference in notation, I'm using nozzle area as A9 dash. There's nothing, it's same as A9. So since we already use A9 for, uh, engine without afterburner, I'm using A9 dash here. Okay. And when we use A9 dash, again, we can assume it's an ideal gas. And if it's an ideal gas, we know rho is equal to P by RT. So we can also substitute that. And if we try to rearrange this, we will have A9 dash to be something like this, where we know T9, P9 and V9 we already found, F, FAB, all these things we already found, m dot infinity is given, which is 15 kg per second. So now if I substitute everything here, uh, what would be the area? So since the uh, velocity has increased, and so the pressure has decreased and temperature has increased, ideally your A9 will increase. Okay, so let me show you. Yeah, so this is your A9 that I'm getting. It is around 0.1003 meters square. Okay, this is the A9 that I'm getting. So compared to 0.0066 meters square, it's almost like how do you say, 1.7 times or so it has increased. Okay, so yeah, let's calculate the exact percentage. So how do I calculate the increase in percentage of A9? So you can use something like this: A9 dash, which is with afterburner, minus without afterburner divided by without afterburner. Okay, and if you do something like this, if you substitute all these numbers, you can find A9 to be something like 52%. So your area has increased to increased from 0.06 to 59 to 52% of increase 52%, basically. That's what I want to say. So or basically you can say 152% of 0.06 meters per. Okay, so your area has increased 52% because of adding an afterburner. Okay, so that's why you need to have adjustable nozzle if you have afterburner in your engine. So when the afterburner is not operative, your area should reduce. So your exit area, you should reduce it to 0.066 meters square. If your area increases, what will happen? Let's say I keep area to be 0.1003 meters square. I will not reduce it to 0.066 meters square. What will happen? Any guesses? Let's say there is no afterburner and I have adjustable nozzle, but my area at the exit should be 0.066 meters square, but I'm keeping it higher than that. Any idea? So it's a adjustable nozzle, like I can keep it higher. What would happen? Okay, that's the food for thought today. Think about it and let me know maybe in the next class. What do you think about it? What if I have bigger area? What happens then? Okay, you can think about it. Let's move forward with the thrust calculation. In the thrust calculation, we already saw when there is no afterburner, we are not adding fuel. The same argument goes as we did for nozzle. Here we have additionally a mass flow rate of fuel in the afterburner. So let's include that also. And your P9 will change, your A9 will change. Here actually it is A9 dash. You should use A9 dash. Okay. And if you substitute all these numbers, you will end up having something like 13.653 kilometer. So you can clearly see when there is no afterburner, you have only 8.116 kilonewton. Now you have 13 kilonewtons, which is a very big rise, right? Almost like 50%. Let's see how much is it. So a percentage increase in T would be a similar formula you can take, T dash minus T by T. And if you substitute that, it will be around 68.2% increase in the thrust. Okay. So please cross check these numbers. Okay. So your area increased by 52%. Your thrust has increased by 68.2%. Okay. Those are the two things. And for the sake of completions, we'll also calculate TSFC. The TSFC would be now not just mass flow rate of fuel in the combustion chamber, it will also include afterburn. So these are the main modifications that you have to do in your calculations basically. So it also, you don't need to remember anything. It's just if you understand the engine, how it works, and if you understand the basic formulas, you can easily relate it. Okay. Now your TSFC will have both mass flow rate of fuel in the combustion chamber and also in the afterburner. So you need to substitute both of these quantities here. So 0.000209 is from combustion chamber and 0302 is from afterburner, and 15 kg per second is m dot infinity that we know. So if you do this, your TSFC will be in this like 5.6 into 10 power minus 5 kg per second per newton, which means kg per second of fuel per newton of thrust. This is your performance of this engine. So here we have written in terms of kilogram per hour per newton. So if you want to do it, what you will do, you want to change this number to kilogram per hour per newton. So in an hour you will have 3600 seconds. So you just need to multiply the 3600 with it. Okay. So it will be something like 0.2021 kilograms per hour per newton. Okay. So your TSFC has increased. So the amount of fuel that you injected also increase, but that increase is more than the thrust increase in thrust that you got. So that is what it is telling here. So your TSFC has increased, and also your thrust has increased. Okay, around 68.2%. All right. Now, what we have to note here is this. We are almost at the end of this problem. Since our exit pressure is critical pressure, it is not same as the uh, ambient pressure. So your point number 9 over here will be a little higher. Okay, so which tells that nozzle is chopped. Okay, so when you draw TS diagram, initially you may not know. So once you complete the whole calculation, you will know where your P9 is. So based on that, you need to change your TS type. Okay, so that is something I want to mention here. And so also we will try to calculate efficiencies. Maybe I will show you the number here. You can calculate it for yourself. For propulsive efficiency, we know it is going to be T V infinity by T times V infinity plus the change in the kinetic energy that you saw in the mass flow rate, right? The change in kinetic energy or the kinetic energy lost because of gas going out of the engine. Okay, that is what this term is. So, I mean, I'm just recapping what we did in the week 1. So, if you substitute these numbers over here, you will end up having propulsive efficiency of 45.65%. Okay, and the propulsive efficiency that you got in your in our last week, we didn't actually calculate the efficiencies, but I have calculated it. I have tabulated it also. We'll see. Before that, we'll also calculate the other efficiencies. The thermal efficiency is something around. So now the thermal efficiency also includes this m dot f AB. So this is a change in the equation, and if you substitute these numbers also, you will end up having thermal efficiency to be 23.59%. And your overall efficiency, you already know it's going to be multiplication of these two, which is around 10.76%. This is your efficiency of your engine in the presence of afterburner, when the afterburner is operative. So now when the afterburner is not operative, what happens is your efficiencies are higher, 54.65%, 28.64% compared to 23, 15.65% compared to, these comparisons you have to do and need to analyze why the efficiencies have dropped. So one thing is efficiencies have dropped. Any efficiencies dropped. And what are the other uh, observations that you can see that A9 has increased, V9 has increased, thrust has increased, and TSFC has increased. All these four has increased. So important thing is thrust and TSFC both has increased. So thrust increase is something that we need, that we want. That's the whole point of doing an afterburner. But with that, TSFC also increases, which means that you are, uh, you know, giving more fuel compared to the thrust augmentation that you are obtaining if it were a separate engine. Let's say if you are able to build a bigger engine which can produce the same 13.653 newtons without afterburner, its TSFC would be lesser compared to the TSFC with afterburner. I mean, compared to the turbojet of this size with afterburner. Okay, so this afterburner is good in that way. With the same size, you can achieve a higher thrust, but also uh, with the increase in TSFC and also reduction in efficiencies. So all the efficiencies reduces. Then the question is why these efficiencies are low in the operative when you have a afterburner in operation. So why do you guys think the efficiency is lower? Can you guys guess what would be the reason? Any idea? So what I would suggest is also you go through once again the week 4 lectures. You will get an idea why the efficiencies are lower. So usually what happens is this combustion happens at high pressure in the combustion chamber. Okay. Whereas the uh, at the afterburner it happens at a lower pressure because the air has already expanded to lesser pressures. So since the pressures are less compared to the combustion chamber, right? So pressure ratio is changing. Or yeah, compare. I mean, when you say pressure ratio, you should uh, tell what is the pressure, which pressure ratio that you are looking at. In an afterburner and combustion chamber, there is no much pressure difference. Only there is pressure loss. But that separate pressure loss are not the reason. Instead, the pressure at the combustion chamber is higher. At higher pressure, you will have a more efficient burning of fuels. But in the afterburner, you do not have high pressure. And since you don't have high pressure, when it goes through the nozzle, it cannot able to it will not be able to accelerate to a higher velocities. So these are the reasons why you have efficiencies very low. And also in the propulsive efficiency is low because your exit velocity is higher. So whenever exit velocity is higher, your propulsive efficiency will reduce. Your exit velocity should be more closer to your flight speed. So if your exit velocity is closer to flight speed, you will have 100% efficiency, right? If it is equal to flight speed, you will have 100% efficiency. That's what we saw. And if your exit velocity more and more different from your flight speed, which means like more and more uh, higher than your flight speed, then your propulsive efficiency continuously drops. And when you add the afterburner, uh, that gets accelerated to even higher velocities because of high temperature, not because of high pressure, because of high temperature. And hence, you will have uh, more reduction in propulsive efficiency. And also, we have thermal efficiency reduced. And because of that, you will have overall efficiency reduced. Yeah. So that's the reason that you have efficiencies lower. So after combustor, best method, more fuel injection in afterburner section, but practically it is very difficult. Um, I'm not quite understanding your question, Tushar. After combustor, best method, more fuel injection in afterburner section. Practically it is very difficult. So would you like to unmute yourself and ask? I'm not sure. What you're thinking?
Sir, my question is means after the combustion over there, some kind of just like in atomic reaction, no?
Mm-hmm.
So there we used to plutonium and this thing reactions over there. So any possibility to put afterburner some fuel injection or some other ignition materials over there in after the combustion or afterburner section over there?
In afterburner itself, you will have fuel injection, right? And there's going to
Yes,
be
yes, sir,
burner.
yes, sir, yes, sir.
Uh,
But in atomic nuclear reactions over there,
okay.
similar principle cannot be applied in afterburner fuel injection.
Okay. So
Then we get the contrast
atomic,
over there.
atomic in the sense, what you're asking? Atomic reactions in
Uh,
the sense?
plutonium with plutonium reaction
Oh,
over there.
okay. So you are telling, can we use some nuclear fuels there in the afterburner?
Yes, sir, yes, yes, sir.
Okay. So, um, uh, see, well, the nuclear fuels, it might be very difficult to use because of various reasons. Uh, One thing
But
is,
not in the micron levels also, the micron capacity or something like that, just like 1 gram or 2 grams like that.
yeah, well, see, you can see there, yeah, yeah. Actually, there is an opportunity. So the main point of afterburner is to increase the temperature. So that is the main point. You can achieve in uh, different ways. Here we are till now how we are achieving is by adding fuel. Okay, by adding fuel and we are combusting it, and upon combustion there will be high heat release rate, and we are increasing the temperature. Um, uh, so what you are telling is we can add some nuclear thing, and uh, but yeah, that is also, you can give it a try. It is something new. So what you can do is you can add some nuclear reactor or something there, which gives more heat. That will actually heat the gases which is coming out of the
Sir,
turbine.
the problem is to control the temperature is very difficult. That's why I said that it's very practically very difficult.
Right, the construction would be very
And
difficult.
once the process start over there, there is no very few chances to control the temperature and
Correct.
pressure over.
Correct. Actually, it is actually possible in a rocket engine.
That is
There
possible
are
in the rocket engine
ra-
by the
there are nuclear
oxygen
thermal
fuel
rockets.
addition of the oxygen over there. Can it is possible in the nautical engines over there also?
Actually, it is not advisable. The reason is radioactive problems that you will
But
encounter.
with the oxygen fuel over there also, which is using PSL 5, that is
Oxygen is not a fuel. So number one is oxygen is not a fuel. But fuel is a which is something liquid hydrogen is a fuel. So people can use hydrogen. So there are few engines which is coming out which uses hydrogen fuel. Um,
so after burner can we inject the hydrogen fuel in
yeah,
that
yeah. So the fuel can be anything, but till now people haven't used hydrogen as a fuel in afterburner. Okay. As far as my understanding, they always use whatever the fuel they use in the combustion chamber till now. Because hydrogen, there is some storage issues are there, right? You
yes sir,
cannot
yes sir.
store a lot of hydrogen in that too. These are for military aircrafts. So the military aircrafts you cannot have that much convenience. You need to you need to look for which is very good in controlling maneuverability and easy thrust requirements. So that is what people look for. If start carrying a high hydrogen tank, it would be a little difficult for them. So it is also a good idea, but it needs some in development of hydrogen storage technologies and hydrogen combustion technologies improvement. So once those technology comes out, then we can actually, as you said, you can include all those technologies in the afterburner.
But sir, in right now current industry of engines, aero engines over there, that electrical propulsion, they are, I think they are going to this method over there.
Yeah, so there are new technologies which is coming in which people are using green fuels, which also includes
Electrical
hydrogen.
propulsion over there, that Elon Musk over there right now is working in the
Right,
electrical propulsion of the aircraft engines over there.
Right, right. So there are new technologies which is which are coming. Yeah, you are right. So people are actually quite interested in developing those technologies, and people are doing, even in electric propulsion, as you said, people are doing it. Yeah. But in terms of gas turbine engine or this course, uh, we won't be going into that much into those things. But yeah, you are right. All right. Any other question? Okay. So these are the some things which I wanted to share, and yeah. So these are the important takeaways that we have upon adding an afterburner. Okay. So mm, yeah. So I think we have solved whatever they were asked for. There is a 52% increase in the nozzle area and 68% increase in the thrust. So that is the final outcome of this, uh, problem solving with afterburner. Okay. All right. Um, if you have any questions, you can ask. But I think with this, I will stop here. I'll be staying here for a few more minutes if you want to ask any questions. So going back, I also want to stress this thing. Um, there is this exam registration coming up, so please do register for the exams, and also please give your full uh, focus, or please give your full, how do you call, what do you call, yeah, try to give your best in this, which which can potentially lead to a summer internship opportunity also with Professor Cherry. Okay. um yeah, and also I encourage you to ask a lot of questions both in forum and in the session. Okay. All right. um you say we'll get back to, yes, Tushar. So um yeah, so basically the questions you asked, I found, I didn't add it in this today's. So I found few, what do you call, a few papers and materials that I found. Maybe I will attach it with the PPT that I have here, and I will post it in the classroom. Sorry, post it in the drive, so you will be able to get back. So basically, the two questions that you have was the H2O concentration, or the moisture content. How does it affect the combustion chamber, right? So in that, what happens is, actually, there are different ways. Uh, One is the effect of pollutants, how it is affecting the combustion chamber. So also includes the moisture. I will share you that, and also uh, what is some interesting thing that I wanted to share is, when they so people usually add water also in a combustion chamber. They try to add water in order to reduce the temperature at the exit, or temperature at the exit of the combustion chamber. So when you add water, what happens is, because of high heat, the water evaporates, and when it evaporates, the overall temperature reduces. So when you have overall temperature reduction, so when you have overall temperature reduction, the turbine entry temperature would be, they might have some turbine entry temperature. They need to achieve a certain turbine entry temperature, but the fuel that they use will always lead to a higher temperature, and because of that, they add some water to reduce the temperature. That also people do. Those are some positive impacts upon adding water. And uh, basically what people usually saw was, there is some startup problems. So when you have a lot of moisture content in your air, it might be little difficult to start the engine. So at the combustion chamber, what you have is, you will have flame holders. That's where the flame will be holding. So you can look at some YouTube videos also. There will be better explanations. So there will be flame holders which holds the flame. Okay, basically that is the anchor points for all the flame. So whenever air comes, it will go through the flame, and when it goes through the flame, it's the fuel and air reacts and then converts to products, hot gases. But when you have a lot of moisture content, these flames get extinguished frequently. So because of that would be, creating a lot of problems when you start it, or when uh, when you're in a climb, or take off, during climb, flight conditions. Those things can happen. So usually when there is a rain, you may need to take off in rain, or you know uh, climb in the rain. So during those time there might be some problems, but people have found better ways to include that. So maybe I will add those papers which might be of your interest. And also I think you also told something about nozzle coating. There's some white color coating that you encountered. um, it looks like it is the nickel chromium inconel coating, I guess. So I'm also not very sure about it. uh, but so actually they use that coating to prevent high pressure and high thermal and high mechanical stresses. So if you put that coating, since you have nozzle going to experience high pressure when you especially have afterburner for, let's say like military jets. We just now saw it's around like 1700 Kelvin is the temperature with which it goes through the nozzle. Um, that is not, but you can also ask why don't we use that kind of thing in the turbine? But turbine also, in a turbine, we cannot go till that much temperature. The reason is, in addition to uh, uh, thermal stress, you also have mechanical stresses in turbines. That's why we always stick with this titanium kind of materials, titanium alloys to for turbine blades. But in afterburner, the nozzle there is only thermal stresses, mainly the thermal stresses, and this thermal stresses can be easily overcome by doing this coating. Okay, so those are the some things. In addition, I also found a paper which has like a lot of aerospace materials that are used in the engine. So there's something that I can also share. Maybe um, with this PPT, the last slide, I will include those materials for you to look over. Okay. But anyway, so you don't need to worry much about those because those are not relevant to our course. Our course purely deals with only the gas turbine cycles and related to the materials and things are not relevant to our course. But you are welcome to uh, ask such questions. It actually widens my knowledge also. All right. GE404 engine. Yeah, I think so. I have to look into it. All right. Yeah, I will share you the papers and materials, Tushar. Any other questions that you have? It's. I see that you have registered for the exam. All the best. Give your full. You give your best out for it. All right. Thanks, Tushar. Good night, Tushar. Bye bye. And it's